In today's video, I'm going to be talking about rotation. Specifically, I'm going to talk about moment of inertia, angular momentum, and conservation of angular momentum. So first of all, I would define moment of inertia as an object's resistance to a rotational or angular acceleration. So the symbol that represents moment of inertia is I. And a common formula for that is the sum of mass radius squared, which is equal to the integral of r squared dm. So next I'm going to talk about angular momentum. Angular momentum is described as how difficult it is to stop an object that is rotating. It is symbolized by this, and a common formula for angular momentum is r radius times p momentum, which is also which can be simplified out into various ways, but aren't super relevant to this to gaining an understanding of angular momentum. Next, I also want to talk about spin angular momentum, or another formula for angular momentum. So another formula is inertia times work. Also describes angular momentum. So I did bring up spin angular momentum, so I'm just going to quickly say what it is. It's an intrinsic property of an object rotating about its center of mass, is known as the spin angular momentum. So like momentum in non-rotational kinematics, momentum is conserved following the law of conservation of angular momentum this time. So now that we have a little bit of this background, I'm going to go ahead and talk us through a problem. So first I'm going to read it. It reads, suppose that a spherical star spinning at an initial angular velocity w suddenly collapses to half of its original radius without any loss of mass. Assume the star has uniform density before and after the collapse. What will the angular velocity of the star be after the collapse? Okay, so since we are referring to a solid, we know that we can just jump straight to the commonly used moments of inertia, which for a solid would be I is equal to 2/5 m r squared. So we know that if it were to collapse suddenly to half of its original radius, let's call this I1, the moment of inertia 2 would become 2/5 m r divided by 2 squared. If you want to relation the two of these, or like show how they differ or how they equate to one another, essentially I1 divided by 4 is equal to I2, which is 2/5 m r divided by 2 squared. So we also know that angular momentum is described by this formula right here. So we can go ahead, which is inertia times the angular speed. And so we can go ahead and do I1 W1 because we know that angular momentum is conserved by conservation of angular momentum. So I1 W1 is going to be equal to, inertia 1 times angular speed times angular velocity is going to be equal to inertia 2 times angular velocity 2. Go ahead and add the vector. Okay, which is essentially the same values as we just got. So I1 over 4, W1 is equal to I2, W2, like that. You solve for W2 using simple algebra or algebraic solution, or like solution solving steps, and you get W, or angular velocity 2, is equal to 4 times angular velocity 1. And then you check if that corresponds with any of the responses, and it does. So option E is going to be the correct answer for this problem. Thank you.